PChem keeps, welcome back to another video. Today we're going to be talking about kinetics and specifically enzyme kinetics towards the end of the video. Okay, so let's go ahead and jump right in. I'm going to talk about something that I mentioned at the end of the last video, which is scattered plots. So we've talked about them a bit in recitation last week as well as in class. So I wanted to point out more specifically what they actually represent. So on your x-axis, you are going to have your protein ligand concentration. And then on your y-axis, you're going to have your protein ligand divided by your ligand concentration. So an important thing to note is we use scattered plots when we don't know the concentration of P. So that's really the reason that we use them in the first place. So some information that you can get from it is actually within the slope. So the slope is going to be equal to -1 over your KD or negative KA. Because remember that Ka and Kd are reciprocals of one another. Okay, moving on to some of the newer stuff that we've learned. So with Michaelis-Menten kinetics. So typically with the Michaelis-Menten model, we have our enzyme and our substrate. And then those go to an enzyme-substrate complex, and then we get enzyme and product. So we have our forward reaction, which is our K1, and our reverse reaction, which is K-1, and then we have K2. So notice that there's not a K-2. So that kind of leads into some of the assumptions that we have. So there is not a reversible step to go back from your product stage to your enzyme substrate stage. So it's irreversible in that direction. Another thing that we should look at is that the K1 is going to be a lot faster than your K2. So that means that your K2 is actually going to be your rate limiting step. So the product formation is what is going to be slower, and therefore we're not going to be worrying about how quickly our K1 brings stuff to the enzyme substrate complex. We just assume that there's plenty for the reaction to move forward. Okay, so if we start with an enzyme and substrate, after some time the rates of formation and dissociation of the enzyme substrate complex will reach a constant value, and this is called steady state. So going a little bit into the math behind this, we have the concentration of enzyme and substrate is going to be constant, which means that our change over time is going to be 0. So if we look back at that equation that we had earlier, we have enzyme plus substrate goes to enzyme substrate complex plus enzyme plus product. So if we break this down into the specific maths of what forms the change over time, again, we said it's going to be 0, and that's going to be K1 times the concentration of E times the concentration of S minus K-1 times the concentration of enzyme substrate complex minus K2 times your enzyme substrate complex concentration. So if you rearrange this so that we're looking just for our enzyme substrate complex, we get this massive equation of the concentration of E initial times the substrate concentration divided by K-1 plus K2 divided by K1 plus substrate concentration. And this breaks down a little bit with looking at our Km value. So this whole section right here actually is equivalent to our Km, which leads into some other equations that we can work with. So if we're looking at the concentration of enzyme and substrate, and we're going to look at the rate or the velocity of the reaction, it's going to be equal to K2 times the concentration of our ES. So substituting in what we had for that last step, we're going to have that the velocity is going to be equal to K2 times the initial concentration of E divided by 1 plus the ratio of Km to our S value. And this is where the Michaelis-Menten equation comes into play, and we actually get this graph right here. So when we're looking at the concentration of S, it's going to slowly build up over time and eventually reach a plateau. So if we look at 1/2 of the Vmax, then that's actually going to give us our Km value. So our Vmax, just to break this down a little bit further, is when all of the enzyme is bound to a substrate. So therefore, Km, like we said earlier, is when half of the enzyme is bound to substrate. Cool. So again, rearranging some of that equation that we had up above, we can get this V naught equals the Vmax times our substrate concentration divided by substrate plus Km. This is just a rearrangement of what we had up top, but it's what is known as the Michaelis-Menten equation. So this doesn't give us a whole lot of data that we can pull out pretty easily. So one of the things that we can do is plot this data, and we can linearize it. So if we take that equation that we just broke out and we do a double reciprocal of it, we get the Lineweaver-Burke plot, which is going to be this equation right here. So when you plot this, you get a 1 over the concentration of S versus 1 over your velocity. And so where the y-intercept is going to be your 1 over Vmax, and then your x-intercept is going to be 1 over Km. And then your slope overall is going to be your Km divided by Vmax. Okay, so the next thing I want to talk about is inhibitors. So looking at this picture, I got this from Khan Academy, but I thought it was a really good description. So this is a normal reaction up on top. So we have our enzyme, and the substrate is coming into this active site, and then it's going to bind, and then eventually you get products out. Pretty simple. With competitive inhibitors, what happens is you have something coming in to bind at the active site, and therefore your substrate is not able to come in and bind to the enzyme. And then for non-competitive inhibitors, you have something coming into something that is not the active site and changing the conformation. So it prevents your substrate again from forming your product. Now, if it requires the substrate to be in the active site in order for it to not happen, that's what we actually call uncompetitive. That's not outlined here, but is another option for a type of inhibition. Okay, so looking at that equation that we had earlier, what do each of these inhibitors contribute? So with the enzyme substrate complex that we were talking about, when we're looking at competitive inhibitors, what's actually going to happen is your inhibitor is going to bind your enzyme, and there's going to be some sort of rate back and forth between your enzyme and your enzyme inhibitor complex. So the K on and K off in this instance are going to be called your Ki, which is just your inhibitor constant. So the next one is going to be our non-competitive. So this is where you can have your the inhibitor come in and bind at the active site, and that's what's going to break down for this part. And uncompetitive has to be bound, or the substrate already has to be bound in order for the inhibitor to work. So again, all of those are going to have different Ki's. And then when we look at the Weaver-Burke plots for each of these, it's going to affect them differently. So for competitive inhibition, what's going to be affected is going to be your Km. For non-competitive, what's going to be affected is your Vmax. And then for uncompetitive, it's actually going to be proportional. So the line is going to move parallel to the no inhibitor present state, and you're going to see a change both in your Vmax and your Km. I hope that makes a little bit more sense, and I will see you guys soon.